Okay, let's dive into this. Welcome to The Explainer. Today, we're completely demystifying modern cloud infrastructure. If you've ever wondered how your favorite apps somehow manage to stay online when literally millions of people log in at the exact same time, well, you're in the right place. We're going to break down the invisible architecture that keeps our digital world spinning, and we're going to do it without getting hopelessly lost in the weeds. Here's our roadmap for today. We're going to start with the high cost of downtime, then move into the cloud-native foundation, directing the traffic, surviving spikes like Netflix, and finally wrap up with the importance of observability. All right, section 1, the high cost of downtime. Let's talk about what happens when things go wrong. Just look at this number. According to a massive study by IJSIT, the International Journal on Science and Technology, a single hour of critical service disruption costs enterprises an average of $1.55 million. That is just a staggering amount of money, and that captures both the direct financial hits and that really hard-to-measure reputational damage. Basically, when your system goes down, it is literally burning cash by the minute. And this staggering financial risk? Yeah, that's exactly why organizations are migrating to distributed cloud environments as fast as they can. See, the old way of doing things was to build a massive system and just kind of pray it didn't break. But the new way, this distributed approach, actually anticipates failure. It just assumes things are going to go wrong, right? So it's engineered to react and adapt on the fly, meaning the end user, us, we never even notice a hiccup. Moving on to section 2, the cloud-native foundation. You hear the term cloud-native thrown around a lot in this space, but what does it actually mean? Well, essentially, cloud-native is a modern way of building applications that are specifically designed to leverage the pure power and flexibility of the cloud. It means you're not just treating the cloud like some remote hard drive anymore. Instead, you're using microservices, containers like Docker, and automated managed services to build software that can handle massive, explosive growth without you constantly sweating over downtime. To really grasp this, we've got to contrast the old monolithic model with the new microservices model. In a monolith, everything is just one giant, tightly connected app. If one tiny part breaks, boom, the whole thing can crash. Microservices, on the other hand, chop that system up into smaller, entirely independent components. And the data from that IJSAT study is actually incredible here. Moving to microservices successfully isolates 91% of component failures and drops full system outages by 64%. Honestly, it's like the difference between a single flat tire completely stopping your car versus a vehicle that, just dynamically reconfigures itself and keeps on driving. Let's move to and see how this builds into section 3, directing the traffic. I want you to just think about this for a second. How exactly do these distributed microservices handle millions of incoming requests all at the exact same time without causing a massive, catastrophic digital traffic jam? Well, the answer lies with the invisible traffic cops of the cloud. And this brilliantly illustrates the solution. We've basically got two main systems at play here. First, a load balancer manages what we call north-south traffic. So that's the external traffic coming from the wild internet right up to your front door. It smooths out those big initial spikes. Meanwhile, the service mesh manages the east-west traffic. That's the incredibly complex internal routing going on between your dozens or even hundreds of microservices. So they work together, right? One guards the gate and the other manages the crowd inside. And look, the load balancer isn't just randomly throwing traffic at servers and hoping for the best. It uses some seriously clever algorithms. It might use round robin to distribute requests sequentially, or maybe least connections to instantly find the server that's currently the least busy, or IP hashing. It can even be resource aware or topology aware, literally monitoring real-time metrics so it only ever routes traffic to perfectly healthy containers. It's a highly intelligent, completely automated sorting system, and it is absolutely vital. Which brings us to section 4, surviving spikes like Netflix. Now, what's really interesting about this slide is how it grounds the whole concept. To quote the Netflix technology blog directly, ensuring a seamless viewing experience for millions of users simultaneously is paramount. Because think about it, when you sit down on your couch and press play on your remote, you expect that video to start immediately, right? Behind the scenes, Netflix has to guarantee that seamless viewing experience, absolutely no matter what kind of crazy back-end chaos is happening. So the crucial point is how Netflix actually categorizes the requests coming from your device. They realized they had to split their Play API traffic into two distinct buckets. The first is user-initiated traffic. This is when you actively hit play. That is absolutely critical. It simply cannot fail. But the second bucket is prefetch traffic. This is the stuff happening silently in the background while you're just browsing around, loading data optimistically to make the app feel snappier. It's totally nice to have, but at the end of the day, it is entirely non-critical. And this exact distinction saved them during a massive, real-world infrastructure outage. Following a disruption, Netflix got hit with a staggering 12x traffic spike, just a wall of traffic from Android devices. If they had treated all traffic equally, the whole system would have crashed, for sure. Instead, their system automatically started load shedding. It's basically like throwing the non-critical prefetch requests overboard to keep the ship afloat. They ended up throttling over 50% of their total requests, which dropped prefetch availability down to just 20%. But, and here is the incredible part, because they prioritized that shedding, they kept the critical user-initiated play availability above 99.4%. The users hitting play literally never even noticed there was a crisis going on. To pull this off system-wide, Netflix actually adapted 4 priority levels straight from Linux. So they have critical work, which is never shed unless the system is basically in total meltdown. Then there's degraded work, which does affect user experience and gets progressively shed as the load increases. Third is best effort work, which doesn't hit the user directly and can be shed during normal operations. And finally, bulk background work, which is just routinely shed all the time. By tying all of this directly to target CPU utilization, the system acts just like a massive pressure valve. It automatically sheds the lowest priority weight first to completely avoid a congestive failure death spiral. It's brilliant. Moving into our final section, Section 5, the importance of observability. You can think of a comprehensive observability framework as your system's central nervous system. It is constantly tracking crucial metrics, things like request latency, error rates, instance uptime, and CPU or memory utilization. And here's why this is an absolute game changer. That same IJSAT data shows that comprehensive observability solutions can detect potential failures an average of 17.3 minutes before any service impacts actually hit the user. It completely flips your defense from being reactive to being totally proactive. I want to leave you with this final kind of provocative thought. 67% of catastrophic failures do not come from a single broken piece of hardware. No. They actually stem from unexpected interactions between completely different components in these massive, complex systems. So the question we all have to ask ourselves is your system truly resilient, actively prioritizing traffic and testing for chaos? Or is it just quietly waiting for the exact wrong combination of events to completely break? Exploring proactive design and chaos engineering is really the next step to ensuring your applications don't just survive the spike, but actually thrive in the chaos. Thanks so much for joining me on this explainer, and I'll catch you next time.